phylogenetic trees.
Okay.
I'm going to talk about phylogenetic trees and Stirling numbers. As you can see, my collaborators are the previous speaker, Péter Erdős, Virginia Johnson, who was my PhD student at the time and currently is a faculty at Lander University, and Anne Kupcok, who is a European bioinformatician, and she's the originator of the problem that we were working on. Phylogenetic trees are essentially trees representing evolutionary processes, relatedness between trees. And as a result, this is something that biologists tend to be pretty passionate about. So much so that my next picture is going to be from the web page of Hillis Lab, where they have a lot of pictures of these phylogenetic trees, and I wanted to pick one. And when I went there, this is what I found there. This is the picture of one of their graduate students from the back. That is a phylogenetic tree over there. So how does this thing look like? Basically, this is how it looks like. You have a root representing the last common ancestor of the phylogenetic units over there. You have the end vertices of this tree labeled with the appropriate phylogenetic unit, which may be species, which may be something larger, in this case larger. And internal points represent points where this phylogenetic unit split into two and form two new different phylogenetic units. And you have, even if you use this representation mathematically, you have two very different, though equivalent representations of the same tree, or maybe more than two. And you have your choice of which one you pick. For my purposes, the second one will be better. What's the difference between the two representations? In one of them, you have a little whisker going upwards, and the point at the end is the common ancestor. On the other one, you don't have the whisker. I don't want that whisker because for my purposes, it's easier to compute what I want to do without those. But those are essentially the same situation, you can see that. So, mathematically speaking, a phylogenetic tree represents the evolutionary relationship between species or other taxonomical units. The leaves, the end vertices, are labeled with the name of the unit they represent, and that is unique. So I don't use the same label on two different end vertices. Now, ideally, such trees are rooted, and I'm only going to talk about rooted ones right now. So you do know which point represents the last common ancestor. Sometimes, for reasons of how we reconstruct these trees, it's very hard to decide where the root should be. And also, internal vertices, not end vertices, represent speciation events. So points where one of the species turned into two species. So non-root internal vertices must have degree at least 3. Degree is the number of lines joining to the point. 1 coming in and at least 2 going out. That's 3 anyway, I count it. And ideally, but not always, such trees that we reconstruct are binary, meaning that there are exactly 2 downgoing edges coming out, because there is no reason for a species to turn into 3 different species at the same time. In general, placement of the root is hard, and available data may not be enough to resolve all trees. By resolving, I mean decide which splits have happened before other splits, so you may have more than 2 edges coming out from any vertex downwards. A species tree or a phylogenetic tree, therefore, for me is going to be a leaf-labeled tree, where the labels occur with multiplicity 1, meaning I don't use them more than once. Root is not of degree 1, and non-root, non-leaf vertices have degree at least 3. So, this is what I want to work with. And there is a connection between rooted leaf-labeled trees and partitions that I want to describe to you. And I realized that I didn't put up the definition, so I should make a picture. A partition of an n-element set, let's just make it something that shows better. N equals to 7, I have 7 points here. What happens is I cut this into pieces. I chose to cut it into 3 pieces. This is my partition. My pieces are called classes. So I have a partition of the 7-element set into 3 classes. One of the classes contains 1 and 3. Another one contains 4 and 5. The third one contains 2, 6, and 7. So I have 3 classes, and the class sizes are 2, because I have 2 elements here, 2 and 3. So there is a connection between rooted leaf-labeled trees, or I should say the counts of rooted leaf-labeled trees and partitions. And in order to describe that condition, I also have to tell you what is an anti-lexicographic order. An anti-lexicographic order is a particular kind of ordering of sets. So I have 2 sets. Say A is 1, 5, 7, and B is 5, 6, 7. And I want to say which one is smaller than the other. And the way to decide it, I look at those elements which are only in one of the sets but not both. Right there. 5 is not good because it's in both of them. 7 is not good because it's both of them. I choose the biggest one amongst them. And whichever set contains the biggest one is bigger in the anti-lexicographic ordering. That's what anti-lexicographic ordering is. It can be shown that it is an ordering in the usual sense, so it satisfies everything that you want something that you call less than satisfy. If A is less than B, and B is less than C, then A is less than C, and sort of things like this. Now, why do I need this? In 1983, 2 of my collaborators, Peter Erdős and László, showed that there is a bijection between the set of ordered leaf-labeled trees with k leaves and n non-root vertices, and the set of partitions of an n-element set into n minus k plus 1 classes. That was a mouthful, so let's just think about it for a second. I said rooted leaf-labeled trees. They are sort of like phylogenetic trees. They are rooted, they are leaf-labeled, but I don't say that they are phylogenetic. Why not? Because I don't have those extra little conditions that phylogenetic trees should satisfy. I can have the root having degree 1, which I'm not allowing for phylogenetic trees, and I can have vertices with degree 2, which I'm also not allowing for phylogenetic trees. But the n vertices, except for the root, are labeled, always. So I take all of these kind of objects with exactly k leaves and n non-root vertices, so the number of n vertices is k, and I leave out the root. I have exactly n vertices in the rest, so I have n plus 1 vertices in the entire tree. And I look at the set partitions of an n-element set into n minus k plus 1 classes. Where does that n minus k plus 1 come from? Well, n plus 1 is the total number of vertices. I have to take off k. So what I'm left with is the number of all vertices that are not leaves, that are not labeled. So what do I need to do? I need to somehow assign the numbers, just a second, 1 through n to all the non-root vertices. So a number to each of these guys, except the root. And I have to assign subsets of these numbers to each of the non-leaf sets that are n minus k plus 1 of them, such that they partition my original set. So that's what I'm going to set out to do. I'm not going to prove that it works, I'm just going to show you how it's done. So here is my handy-dandy tree, and you can see it is not a phylogenetic tree. I have, the root has degree 1, I have a vertex of degree 2 there. It doesn't have to be that way, it could be a phylogenetic tree, but just for illustration. So I'm gonna, let's just say first time what I'm gonna do. I'm going to assign sets that contain elements of the label to every vertex here. How am I gonna do that? For each leaf I assign a set containing just its labels. Okay? And for any vertex, say to this one, I look down which leaves are below it in the tree, and the set corresponding to that vertex will contain the labels of those leaves. Right there. I'm not worrying about the root because I need n of these, and there are n plus 1 vertices there. The root is extra. So what I'm going to do, now there is something important here. Sometimes sets may repeat, because this is the set containing just one element A, and this is the set containing just one element A. But I'm going to look at these sets, and I'm going to order them according to that anti-lexicographic rule I have up there. This little 2 down here means that I have the set containing just A repeated twice. And I'm going to assign numbers to each of these sets in the order they appear. So the set containing A will have the numbers 1 and 2, and all the rest will have the rest of the numbers accordingly. Now these three had 1, 2, 3, 4, 5, 6, 7, 8, 9 vertices. N is the number of non-root vertices, so n was 8, right? I have 8 numbers there in order. And I'm going to transfer these numbers back to my tree in place of the corresponding set in such a way that if I have repeated sets, like AA here, the smaller number is below the larger number. This is going to be a unique way of putting those vertices. So now I have my numbers. What do I need? I need to partition the set 1 through 8 into n minus k plus 1. N was 8, k was 4. So n minus k plus 1 is 5 partitions. And this 5 actually corresponds to the non-leaf vertices, so nothing that has that sort of funny orange color. The blue one and the yellow ones. What do? I look at those vertices, and I look at what number is right below them, connected with an edge. Those are going to be my sets. So this vertex has just the number 1 below it, so it's the set containing 1. This vertex has 3 and 4, set containing 3 and 4. This vertex has 5 and 6, set containing 5 and 6. This vertex has 2 and 7, and this vertex has 8. Because of the way I did this, any guy here is just below one other guy, so he cannot be in 2 different sets. That ensures that what I create is actually a partition. It will cut my set up. There will not be overlap. So this phylogenetic tree gave me that partition. And it has some very specific properties. A parent's index, a parent is somebody who is right above a node here. A parent's index is the maximum number of children plus 1. The class size of any partition is the corresponding number of children in the tree. And ordering of the leaf labels are preserved by this numbering. The original ordering was A, B, C, D. They are in this order. The numbers of the leaf are 1, 3, 4, 6. Same ordering. So I'm going to use this property. This was the partition I created before. I can go back to the tree. How? These were the properties. The parent's index is the maximum index of the children plus 1. That means the root's children are precisely in the set that has the largest number. So the root is connected to 8. Now, the parent's index is maximum index of children plus 1, so the children of 8 is in the set that contains 7. So they are 2 and 7. The children of 7, set containing 6. Children of 5, set containing 4. Children of 2, set containing 1. Here's my tree. Ordering of the leaf labeled preserved. I put back look at the numbers on the leaves. Oops, I'm going the wrong way. And I put back the leaf labels according to corresponding order. This is precisely the tree from which I started. So this is a correspondence. I can go backwards and forwards in the right way. Now, I'm going to have some further definitions. Sorry, this is how math goes. F of nk is going to be the number of rooted leaf-labeled trees with k labeled leaves and n non-root vertices. These are not the phylogenetic trees again, because the root may have degree 1, internal vertices may have degree 2, which are not allowed in the phylogenetic trees. But these are objects I can count, and Fnk is the number of counts, the number that counts them. Snj is the Stirling number of the second kind, which counts the number of partitions of an n-element set into precisely j partition classes. What Erdős and Székely showed you, and what I illustrated before, is that Fnk, the counts of the rooted leaf-labeled trees, is the same as the Stirling number of the second kind, Sn n minus k plus 1. And they showed it with the bijection under which odd degrees of non-leaf vertices in the tree correspond to class sizes in the partition, which is going to be very important for me later. And that means that any results on Stirling numbers of the second kind translate to results on counts of these leaf-labeled trees. And there are many results on the Stirling number of the second kind. For example, Dobson showed that this sequence is unimodal for a fixed n, meaning there's a unit maximum. They increase first and decrease then, and they don't turn around again. This sequence is strictly log concave, which is a technical condition, but it implies unimodality. And I need to talk about normality results because that's what I'm going to get into soon. So I have what's called a combinatorial array Nj. What's a combinatorial array? You have an infinite sequence of finite sequences. Wow. So you have a 0th sequence with a certain finite number of elements. Then you have a first sequence with a certain finitely many elements. You have a second sequence, may have less number of elements, and so on. But there are infinitely many of these finite sequences. I'm going to define this quantity E sub n, which is E sub n. You just add up the entries in the n sequence. Why do I need that? Because now if you consider the normalized version of the sequences, they add up to 1. That can be considered a probability. Then these guys can be coming from a probability distribution. So I'm going to define my random variable z sub n. So for every sequence I have a random variable z sub n, which takes values of integers. The n sequence has value, first sequence, 0th sequence has value 0, 1. First sequence has value 0, 1, 2, and so on. So the values depend on the length of the corresponding sequence. And the probability that this z sub n takes the value of j is precisely the jth entry in the n sequence divided by E sub n. Because of the way I created these numbers, this is going to be a perfectly good probability distribution for each of those sequences. Now, the original combinatorial array E sub A sub nj is called asymptotically normal, if that holds. What in the blue blazes does that mean? So what it means is fairly simple. It means if we create the cumulative density function is of z sub n, which means I just count what is the probability that Z sub n is at most J? And I write it up. And I make the corresponding table for it. This looks something like this. What does that mean? I add up the values of the n sequence, say for this guy, values of the n sequence for the first 3 values, or first 4 values because I started from 0, and divided by E sub n. This is exactly the fraction I have. So it starts from 0, gets up to 1. What fraction of the total value has been encountered up till the J point? This is a nice, simple thing, easy to do. This is going to start from 0, ends up to 1, and will have some shape. And as n goes to infinity, this shape will look more and more like the cumulative density function of the normal distribution, appropriately normalized, which is, I'm not going to put this entry because the appropriately normalized part, which is sort of like this. And I can tell exactly what is that curve that it gets closer and closer to, which will help me to even not tell these values exactly, but at least approximate them. In 1967, Harper showed the asymptotic normality of the Stirling number of the second kind, and in fact, he told us exactly what the expectation and the variance of that random variable is, where B sub n is now the total number of partitions of an n-element set, so the sum of the S of nj's. In 1977, Canfield showed a local limit theorem kind of version of this, that asymptotic normality, so what we had before, strict log concavity, and the fact that the standard deviation of this random variable goes to infinity as n goes to infinity implies this condition, which again I can tell you much more easily if I say that if you just simply make this sort of bar graph for the entities A sub nj. So n is fixed, and this is j equals to 0, j equals to 1, and so on. Then this shape will be well approximated by the normal curve, the bell shape, which means that you can approximate them in a slightly more precise way even. So what's the Harper-Canfield method to show asymptotic normality? Consider the generating function of this array. This is how it looks like. So this is my constant term. This is x. This is for my 0th sentence. This is constant terms x squared. That's my first sequence, and so on. You write up nice polynomials like this. Then you can easily tell what the expectation and the variance of your random variable will be using this function and its derivatives. This is a fairly easy exercise to show improbability. If you can show that this polynomial has only non-positive real roots, which is the heart of the matter if you try to show something here using this method, then you can consider Z sub n the sum of independent Bernoulli random variables. Bernoulli random variables are sort of like throwing a coin. It either lands head or tail, so 0 or 1. And it may be a biased coin, so it might have a tendency to land on head or land on tail. That's the only thing. Why is it important? It is important because when you have sum of independent random variables and you add them up, they usually tend to go to the normal distribution. If you have taken statistics classes, you will see that happening. And you just have to check a few conditions to make sure that they do. And in fact, a version of the Lindenberg-Feller theorem, which is a nice complicated theorem, implies that it's enough to know that the variance goes to infinity as n goes to infinity to show that this sum is actually indeed asymptotically normal. And I have the variance up there. I can compute it once I know what the generating function is. So we have a method to do this. And if we also know the strict log concavity of this sequence, we have the local version, which is slightly stronger. In order to do this, because we are talking about the Stirling number, I have to add up the nth Stirling number for each value s of nj, and that's the nth Bell number, which is the number of partitions of an n-element set. And I have to know something about those. In 1955, Moser and Wyman showed asymptotic for B sub n, and what was more important for us, in 1994, Canfield showed this, again, quite complicated formula. But things here are, it depends on n. It's a solution r times e to the r equals to n for every n. This is B sub n plus h, and h can vary. H has a quite large range in which this asymptotics is valid. It's important for us because we'll have to consider in our proof, which I'm not going to show, don't worry, things like B sub n times B sub n plus 1 divided by B sub n plus 1 times B sub n plus 4 for different possible values of h. So we need something where that n is fixed, and I can use them in the formula, and this works. So this is a very useful thing. And we can exactly tell the order of r. So how good this is. We can show that the Stirling numbers actually form an asymptotically normal array. So what does that mean? If I make that little bar curve of the Stirling numbers, it should look like a bell curve as n goes to infinity. But this is a limited result. Why is that important? It's important because, well, I do for n equals to 1, it's not going to look like normal. N equals to 2, it's not going to look like normal. How far do I have to go before this actually means something, before it does look like normal? And I don't have to look very far. N equals to 15. This is an actual count. The dots represent actual counts of the corresponding Stirling numbers, taking it quite large, as you can see. It's a little bit of cheating because I should have put bars there instead of these smoothed things, but I don't know how to do that, and I wasn't willing to learn. But what happens is that I will overlay this with the appropriate normal curve. The fit is quite good, isn't it? Very nice. But these are Stirling numbers corresponding to leaf-labeled trees that are not phylogenetic trees. We were interested in phylogenetic trees. Let's remember the LCK bijection. We know this, and we also know that under this bijection that they showed this with, odd degrees of non-leaf vertices correspond to class sizes of the partitions. What's a phylogenetic tree? A phylogenetic tree means that every internal vertex has at least two things coming out of it. So the corresponding partition, the class size in the corresponding partition has to be at least 2. That's the only extra thing I have to add when I count my partitions. I can't have partitions where, when I chop up my set with this partition, one of these parts have just one element in it. That's what I'm not allowed to do. So I'm going to denote by S star, after all it's a version of those Stirling numbers, the number of partitions of an n-element set into k partitions with the extra condition that each partition class has size at least 2. And Bn star is the total number of such partitions. After all, it is a version of the Bell number. And F star nk is the number of looted leaf-labeled trees with k labeled leaves and n non-neutral vertices. So far so good, the same thing as before. But out degrees of non-leaf vertices where the branching is occurs should be at least 2, because that's what makes a phylogenetic tree. So F star nk, with other words, is the number of phylogenetic trees with k labeled leaves and n non-root vertices. Those are the things I'm interested about. Now, the average CK bijection gives me that the equation I had before holds for the start version as well. I don't have to do anything for that. Thank you, by the way. It's an easy exercise for math grad students to show that the start Bell numbers and the normal Bell numbers correspond to each other this way. And this equation follows from that. And we can use whatever we know about the Bell numbers to compute the expectation and the variance of a relevant random variable about which we want to show that its distribution tends to normal. And we can show using the method that I told you about before. You do not want me to go into the details, I'm sure about that, that the corresponding array S star and M is asymptotically normal, and the generating polynomial has different non-positive real roots. The variance goes to infinity as needed, and so on. What does this mean? This means that if we fix the number of non-root vertices, so the trees that I'm interested in have the same number of vertices, and count the number of trees with k internal vertices. So k is my variable that changes, and the total number of vertices is fixed, and make this picture with the counts. It will tend to normal. Let's see how well this goes. I showed you S15K, the picture of S15K before. This is S star 15K, 16 minus K leaves, and K internal vertices. I count the phylogenetic trees this way. This is the overlay. Well, this is not going to look so well, right? However, let's be a little more fair. Now I actually halved my possible data points because K, the possible values of K range from 0 to 8 now. So I actually halved how many values I have. So it would be a more reasonable comparison if I would look at S30K, and the overlay looks a lot better. So actually, that convergence that I'm caring about is still pretty good. But this is still not what the biologists care about. What they really want to have, I have my species. I'm creating the tree from that. So the number of leaves which corresponds to my species is the one that's fixed, not the total number of vertices. So what they care about is this. The number of leaves of the tree are fixed, and the number of non-leaf points may vary. And this is how my count should look like. I fix the number of trees, vary the number of non-leaf points, look at how many different ways I can make a tree with that many leaves and that many non-leaf points, and make the count. So I'm going to denote by T sub n plus 1 m, because n is always, for me, what is fixed. It's the number of trees with n plus 1 leaves and m internal vertices. It can be easily shown that T sub n plus 1 m corresponds to my previous counts this way. So what I'm really interested in is the distribution of the starred version of the Stirling numbers for n plus m, where n is fixed and the range of m is 1 to n. You may want to ask that, okay, so if this is what I'm interested in, I can go back to my usual trees that are not phylogenetic. But the problem is if I look at the unstarred version of these things, then the range of m is from 1 through infinity, so there is no way I can do this. So even though mathematically this might be interesting if it was a reasonable question, it is not a reasonable question. We can show what the expectation and the variance of the corresponding random variable is. And the blue dot part was known already by Flageolet. He probably could have done the rest too, but he wasn't interested with were. And we can show that everything is still fine and dandy. Everything focused from before. So we can actually, with this, have asymptotic counts for any n, the number of n leaf trees with that many internal vertices, which is something the biologists are interested in. And this is a plot for 16 leaf trees. The fit is not so good, but if I increase to 31 leaf trees, the fit becomes much better. So actually, the convergence is good enough. This can be used in practice. And that's all I wanted to say. Thank you very much.